In this video, I'm going to show you how to apply Newton's law to multiple objects when they are connected. The connection can be modeled usually by spring and damper. To model the spring, we use Hooke's law. Now let's look at this figure. This is the position where the spring is relaxed. We can call this position equilibrium. Now we would like to stretch the spring by pulling this end to the right by a displacement x. Let's assume this end of the spring is fixed. Then there is a restoring force applied to this end in this direction. How large is this force? It is Fs is equal to K times the displacement x. Since the direction of this force is to the left, so we use a minus sign. K is a constant. It is character of the spring. If we further stretch the spring, as you can see from this figure, so the relationship between the force and the displacement is non-linear. As we mentioned at the beginning of this chapter, most physical systems are non-linear, but within some range, it is linear. The same when we try to compress the spring by the displacement x from the equilibrium. Then there is a restoring force from the spring applied to the right. Since x in this case is minus, so the force is minus kx. It is positive. The direction is to the right. As you can see from this figure, when we further compress the spring, then the relationship between the force and the displacement is no longer linear. The same principle applies when both ends are free. Let's draw a spring. Suppose the length of the spring is x1. When we try to stretch the spring, let's assume now its length becomes x2. Then we know there is restoring force applied on both ends. The property that the restoring force at both ends are equal, but with opposite directions. How large is this restoring force? Let's use F. First, let's not worry about the direction, just about the magnitude of the force. So F will be equal to K is a constant, is a character of the spring, then times the changes of the spring. It will be x2 minus x1. Now let's consider the case when we compress the spring. Now the length of the spring is x2. Then we know there are restoring forces at both ends. According to the property of the spring, the restoring force are the same magnitude, but with opposite directions. What is the size of the restoring force? Again, let's not worry about the direction. So only about the size, the magnitude. F is equal to K times x1 minus x2. The same principle applies to the damper. We use this dashpot to represent the damper. The damper is different from the spring. The magnitude of the force is assumed to be proportional to the rate of change of the relative displacement of the two ends. Let's say if we fix this end, when we try to pull the other end by a velocity of v in the direction to the right, then the friction force from the damper will be in the direction to the left. The magnitude of the friction force is Fd minus Bv. B is friction constant. The same when we try to push this end of the damper by a velocity of v, then the friction force from the damper will be in the direction to the right. Then the magnitude will be minus Bv, since V will be a negative value because it is to the direction of the left. The same principle applies when both ends are free. Then we can calculate the relative velocity. The relative speed. Then we can still use this formula. When we try to analyze the motion of multiple objects when they are connected, we can still use Newton's law. In this case, it's very important to draw the free body diagram. Then we can analyze the external forces and internal forces. For the internal forces, in general, they are applied in an opposite directions. In both directions with the same magnitude. That's because are the property of spring and damper.